I had to reset something and wasn't recording. The physics part will be recorded. But Meredith, the piece before definitely will be on Twitch, on the Twitch recording. I had a question from Siddiqui about quiz 1 grading. If there's still something off with your quiz 1 grading, contact me, contact your grading TA, and we will get it fixed. We do ask that everyone submit, if something happened and you couldn't submit your quiz to Blackboard, email it to us, but also submit it to Blackboard. We need it both places. And we'll get everything fixed up for you. Okay, so I'd like to talk now about physics. So first question, we have plenty of time. We have plenty of time before the next exam. We have plenty of time to make sure that everyone is understanding things fully. So is there anything we did last week in recitation, or was there anything from your most recent homework set that you didn't understand? Anything you'd like to talk about now? Would you like to ask us questions about homework 3? Would you like to talk about last week's recitation? Physics is cool, says Walter actually can shred on the guitar. I am a terrible guitarist. Really, a guitar lives in my office because I want to demonstrate physics of vibrating strings to students. I am a choral singer. I'm a piano player. I'm not a guitarist. Yes, if you want to drink tea, you can bring tea once everybody gets vaccinated. Tilting the axis and number 3 from homework 3. Okay, so everybody wants to talk about homework 3. So let's do this. Lucy Storm says, I love these lectures. They're so peaceful. We can play like peaceful music, or we can play grouchy music if you want. We can have. How about this? You all tell me at the end of class. Tell me what genres of music you would like next time, and we can play metal. We can play EDM. We can play whatever you like. We can even play TikTok memes. Okay, so let's dig up homework 3. So homework 3, problem 3, that's the one I thought it was, is the one about the locomotive. So what's going on here? So remember, our scheme for addressing any of these questions is always first cartoons and diagrams, then Newton's laws, and then finally algebra. So I will talk about step 1 here. I will leave the other 2 steps for you all to do. I'm going to adjust something on the camera for just a moment. We're set a little bit too bright. I'm dealing with the fact that I'm in a different place and different time of day, so we have lots of light coming in from that way. And I need to try to get that sorted a bit. That'll help a little. Okay. So we're on ground here. We have a locomotive in the front. We know it's a locomotive because we'll draw a little smokestack on it. And it's pulling 2 train cars. You can make fun of my art. We used to have a head TA who went to art school, but she is not here anymore, and now you have to deal with my crappy art. Our head TA who went to art school is the same one who had Kiki the cat. So here is our cartoon, but now we need to think about the forces that act on these things. So tell me, what forces act on, we'll draw 3 diagrams separately. We'll label these as locomotive, car 1, car 2. So let's go one at a time. What forces act on the locomotive? I should add a music suggestion tab on Discord. Adam, if you are here, could you add a music suggestion, a music channel on Discord? Make it go, Adam. Traction and C1. So as we'll see today, friction, or excuse me, traction is a special case of friction. We'll label this F traction. So there's no separate friction force on the locomotive, like retarding its motion, because the friction force between its wheels and the rail is actually what makes it go forwards. So Luke has said force of friction, force of locomotive forward, and force of car one backwards. The force of friction is the propulsive force forward. You might imagine taking a locomotive and asking it, like putting ice or oil on train tracks, and then the locomotive would not be able to go, right? You can imagine a locomotive just sitting there spinning its wheels on rails that were slippery, right? So we kind of intuitively know that the propulsive force forward really is a kind of friction. Now, we haven't explored that in depth yet. That's today's topic, but you know enough to be able to do this problem. Wait, what's L1? Yeah, good question. Why have I labeled this L1? So an important thing whenever you're doing anything is to think about what your mathematical notation means. So this arrow, what this represents is the force on the locomotive from car 1. Can you all read that text okay, or is it too small? So we'll label this as FL1, force on locomotive from car 1, but I'm going to use this symbol for it algebraically. FT question mark. Bouncy Ball says, is that the same as tension? Yeah, if you think of this as a rope, then it would be tension in that rope. If you think of it as a coupler with the two train cars connected by interlocking metal parts, then it's a normal force. I'm going to adjust something on my broadcast setup just to make it easier for me to read Twitch chat without having to leave the board. There we go. Why isn't it car 1 and car 2 though? So this is the same moral of the story as your recitation problem from last week. Car 2 isn't touching the locomotive, right? So these are forces on the locomotive. So now we need to draw diagrams for the other two cars. We're not done yet. So what forces act on car 1? Yes, I have set the camera to, rather than tracking my face, because you don't care what I look like, I have set the camera to remain focused on the board all the time. Okay, so if I'm thinking about car 1, let's see, what have people said? Locomotive goes to the right, car 2 goes to the left. Yep, so to the right, this will be force on car 1 from locomotive. And going to the left, this is the force on car 1 from car 2. Anything else? Any other forces that act? Yes, friction here. So car 1 is not trying to spin its wheels, right? There's no locomotive turning car 1's wheels. And the axles in the wheels, the bearings, and the contact between the wheel and the ground will slowly slow it down by a process called rolling friction. We're actually not going to treat rolling friction that much. But there is a frictional force that goes to the left. And as before, rather than writing out all of these words, we can write symbols. Now, you could draw something very similar for car 2. Before I do that, though, I want to address the comment in chat. Porpoise says, friction because the car has no traction force. Said Ferret Boy says, you want friction on the locomotive. You do not want friction on car 2. Yeah, so when we're trying to build a train, the wheels of these back cars can spin freely. And we like them to spin freely, so there's no friction arresting the motion of these. But the locomotive's wheels cannot spin freely. They're connected to a motor that tries to turn them. So the friction force between these wheels and the rails is actually what propels the whole thing forward. Luke says, I thought the force of friction was always in the opposite direction of motion. It's in the opposite direction of relative motion. And we're going to talk about that today in like 15 minutes. Shine Wi-Fi loves sabotaging my learning. Jiffy Jules, if you are having internet connectivity trouble, then turning off low latency mode will help. Another thing that you can do in Twitch is if you click on the little gear that says settings, there is an option for quality. It defaults to 1080p. If you set it to 720p, it will save you a fair bit of bandwidth, and you should also still be able to read things. It is not Thomas the Tank Engine. We'll do Thomas the Tank Engine next year. You want more cacti. Cacti will come back. So for car 2, again, I let you draw these in. I'll let you think about what forces act on car 2. But thinking about this clearly gives you a list of all of the forces acting on each object. Then, all you need to do is, all right, you did step 1. This is actually the hard part because it involves thinking clearly. Mathematics is just a sort of a rote thing. You can take a look at your force diagrams and write down Newton's laws. So here, for instance, I've got this force in one direction, that force in another direction. I'm not going to do that for you, but you'll wind up with 3 equations. The sum of forces equals ma for the locomotive. The sum of forces equals ma for the first car, and then, as I try to deal with all of my colors of chalk, the sum of forces equals ma for car 2. This will give you 3 equations. Do all of these objects have the same mass? No, they don't. So here I've written this down, but you have to think carefully about what you use for your masses. Do all of the cars and the locomotive have the same acceleration? Yeah, they do, because they're all part of the same train. They all move together. So you have to think clearly here. And just as you did last week in your recitation, some of these forces will be the same by Newton's third law. So make sure you take advantage of that to reduce the number of unknown things you have. The sun keeps changing, so I need to adjust that. Maybe I can just close the blinds. Sorry, y'all. Oh, that helps. So yeah, the masses are m and 3m, so they're different. Now, in all of these problems, yes, the acceleration is, we'll do this, see if that helps. Yes, the acceleration is not something, or is something you know and you're trying to figure out forces, but that's fine, right? When you construct this system of equations, it doesn't matter what's known and what's unknown. Construct the equations, and then when you get over to doing the algebra, here, you just put in what you know. In this case, you know the masses. What did I have you solve for? And you know the acceleration. Solve for what you want. In this case, what you want is the traction force. Now, this process here is called solving a system of equations, where you're going to wind up with 3 equations and 3 things that you don't know. You studied this in school, I imagine. If you didn't, that's fine. We come to the physics clinic and we'll do a complete review on this math idea. But to solve a system of equations, there are lots of different techniques that students learn for solving systems of equations, lots of things that you can do, but only one of them is really useful. In our class and in many science and engineering classes, using substitution is almost always the best way to do this. So what you will do, for instance, is get an expression for the force that car 1 exerts on car 2, and then substitute that into one of the other equations, to equation 1, to get an expression for the force that the locomotive exerts on car 1, and then substitute that back up here to get an expression for the traction force on the locomotive. This business of like multiplying an equation by something and then adding the 2 equations together, yes, it's valid, but don't do it. It's always way harder. It's a thing you can do, just it makes the math hard. Porpoise says, I wished I'd learned that from the beginning. Yeah, so the business of like multiply the equation by -2 and then add them together and make stuff cancel, it's just really not that useful. Luke has said, can we go over car 2? Well, you tell me. What forces do you think act on car 2, on this little orange one in the back? Car 1 to the right, yep. So force on 2 from 1. And what else? Friction. And which way does friction go here? Yeah, to the left. Somebody has figured out how to write arrows in Twitch chat. Very cool. But little lost on the back. Yes, it's friction again. Here, we could write this as F1L, right? So I've done the hard part here for this problem. I want you to reproduce it on your own. Um, don't just copy my diagrams, don't just copy this, but I wanted to talk through this process of thinking, okay, what actually pulls on this or that object? Notice there's no force on locomotive from car 2. Only thing it's connected to is car 1. But yes, the locomotive is pulling everybody, but the laws of physics will take care of that. Is the friction the same on both cars? Yes, the problem tells you that each car experiences the same backward force, F sub F. Any other questions about this problem? We'll get out of the way and let you all take a peek. Bouncy Ball says, how is it that the net forces for car 1 and car 2 are not the same if they have the same mass and acceleration? That's a really good point. So let me erase this. So for car 1, you're going to have the sum of the forces on 1 equals ma, and car 2, the sum of the forces on car 2 equals ma. And what Bouncy Ball has pointed out that wait a minute, these right-hand sides are equal because both have the same mass and both have the same acceleration. So Bouncy Ball is thinking, well, wait a minute, if the right-hand sides are equal, then so are the left-hand sides. Yes, they're both going to have the same net force. So what that tells me then is whatever these two arrows add up to has to be the same as what these arrows add up to. And by representing that algebraically, you can figure out how big these arrows have got to be. So yeah, you're right. These two sums are the same. But you'll have to put in what goes here and do the algebra for yourself. Car 1 has 3 forces acting on it. Yes, it's being pulled forward by the locomotive, it's being pulled backward by the car behind it, and there is some friction in its wheels. And porpoise, yes. Friction acts on everybody, as I think the cool kids say, but the locomotive's wheels are being turned by its motor. They're not just rolling freely. Something funny is going on in these wheels. It's got a large traction force going forward for its friction just because its wheels are being propelled. And Sad Ferret Boy has given us an explanation of how rolling motion works. I'm going to talk about that in a bit. Yes, that's an adequate explanation for traction. That's exactly right. Exactly right. Eddie has written something. You wrote we know acceleration. How do we know the acceleration in part 3? We're given its acceleration. How do we? So basically what Eddie is saying is, I just said, hey, the acceleration is this value alpha. So here's kind of a thing about physics and engineering. Often in engineering and physics, we're not interested in understanding only one machine. We're interested in understanding every machine of a given type and design, regardless of how big it is. So as an example, if you're trying to calculate, say, how far a thrown ball would go. So if I open my window and I were to yeet something out onto the quad, I could do the calculation once for a particular initial velocity. Or I could say, let me try to understand where a snowball would land on the quad for any initial velocity and angle and so on. So often when you're solving problems in science and engineering, you're interested in getting an answer in terms of all of the variables that you might start with. So if you're a train engineer, you might be interested in saying, okay, how hard does the locomotive have to pull for any value of the masses of the cars and for any acceleration the locomotive wants. You'll get a different traction force depending on how hard the locomotive wants to accelerate the cars. So your answers here will be in terms of alpha. I'm going to click back to this. So notice here the way this is written. I'm just going to highlight some text. So this text at the beginning, a locomotive with mass such and such pulls a train consisting of two cars, each of which has a mass of m. The locomotive wants to accelerate them forward at an acceleration alpha. Each car experiences a backward force f sub f. These are variables that should and will appear in your answer, right? Anything like this that is given to you in the problem is one of the things that you'll be calculating an answer in terms of. Yes, you don't have a number value for it, but that's okay, right? The great genius of the invention of algebra is to allow us to calculate with things, even if we don't know what number value they have yet. So Eddie, does that answer your question? Great. Okay. I would like to, just in the interest of making sure everybody has what they need for recitation tomorrow, I'd like to shift and talk about friction. So friction is a really complicated subject. It depends on the minutia of what surfaces are made of. Oh, dropped my eraser. Thankfully, I have another one. So you might imagine all kinds of really complex frictional forces. So for instance, if I have a ratchet, if I have something that's shaped like this, and then I have something else that's shaped, well, in the opposite, like so, you might imagine that these two objects can slide past each other far more easily in one way than the other. So going this way is hard. Going that way is easy. So the details of friction depend often, or they can depend in super fine detail on the particulars of the surfaces. But most things are not that hard. Most of the time, there's a simple model that we can easily calculate for friction. So in general, here's the idea. Anytime two objects exert a normal force on one another, then, so let's think about what that means. I'm going to kind of construct little doodles of what we're talking about. So if I, for instance, have a table here, and I've got an object sitting on that table, well, I know that because they're in contact, well, the table exerts a normal force on that object. But anytime that happens, there may also be a frictional force that opposes their relative motion. So what that means is that when that happens, let's just draw this again. I've got my object here. That means that there could be a frictional force this way, maybe. Or it could go the other way. But regardless, it opposes their relative motion to stop them from sliding. Let me just catch up with what people are typing. So Kongplash wrote something about my ratchet example of the details of those shapes. Yes, going left would have been hard there too. Going right would have been very hard. And Christopher Vinn says, yes, it would be less hard. But yeah, so Yulun has kind of gotten to the heart of this. How flat do the surfaces have to be? Well, that's a tough question, right? So what we're doing with friction here, this is not in the fundamental laws of physics. This is an empirical model, a thing that we observe that gets pretty close for most sorts of surfaces and most values of the normal force. So it is very close to valid for things like car wheels on pavement, car wheels on ice. What would another example be? Shoes, like boots on terrain that you hike on. But it probably would be less valid for things like microspikes or crampons on ice, where you're actually spiking into the ice as you walk. People who've lived in Syracuse for a while, if you're not from here, many people have basically spikes that they wear on their shoes so they can walk on ice without falling. So what we're learning here is a model that is pretty close to accurate for a lot of things. And Yulun says, how flat do they have to be? Well, the flatter they are, the more regular they are, then the better this model works. Yeah, so Maxiplier, you're from Phoenix, as I recall, right? So I also learned to hike out west in Arizona, in Tucson, where the challenges of getting around are rather different. It's don't fall on the cactus and don't run out of water are the challenges in the desert, and they're kind of different here in Tucson and Syracuse. Sad Ferret Boy says, isn't friction due to the surfaces not being perfectly flat plus chemistry stuff? Yes. So what we're going to talk about today is an approximation of the combination of these micro-level effects that happen between two surfaces. So really, like if we were to kind of magnify this, if we were to take this and magnify it, what you would see, right, would be kind of a not perfect surface, a jagged top to the table and a jagged bottom to the box, and those little bits of roughness stick into each other as things slide past, plus you get these chemical forces like the van der Waals force and hydrogen bonding and a bunch of stuff I don't understand happening at the surface. So it turns out, though, that we can absorb all of the details of what's going on in that surface into one number. So what we're going to do, I'm going to erase this now. I'm going to keep this, and we're going to talk about two cases. And as I said at the beginning of class, the trade-off between these two cases of sliding friction and sticking friction are what makes the violin work. So the two cases that we will explore, the first one is where the surfaces are sliding and friction opposes them sliding. The second case is when the surfaces are not sliding and friction I'm running out of room here, keeps them from doing so. The names given to these are kinetic friction and static friction. And something to note is that when I write sliding, this means, I'm searching around for, got all of my colors of chalk out except red or pink. I wanted pink. Sliding here refers to relative motion. Okay, so what we're going to do now is we're going to talk about how each of these works in turn. So Sad Ferret Boy says, in the ratchet example, if the two surfaces are both vertical and the motion is tangent, but bringing the two surfaces forward toward each other, isn't that normal force opposing the force of motion? Yes. So let me pause. Sidebar here. When I was an undergraduate, I thought that my development in physics would be I would, take all these classes and learn the laws of physics, and then get really good at math, and then I could calculate anything with the laws of physics. That's how I thought my education would go, is that I'd learn the laws, and then I'd get really good at math. Anybody who knows me knows that I'm not really good at math, so clearly something else happened. Instead, when I got to my PhD program, what I learned was that real skill in physics, which we're all, growing in, is not the ability to calculate a thing, but the ability to understand when to approximate a thing. So Sad Ferret Boy has pointed out that if I have my ratchet, right, if I had the thing that I drew earlier that looked like little teeth, and then I had another thing that looked like little teeth, and I were to press those two together, or if I have, some surfaces that are kind of bumpy, and I try to press these together, that really the forces at play are normal forces, right? As these protrusions fit into each other and try to move through one another. But if you're going to do that, if you're going to try to figure that part out, then to understand, say, tires rolling on concrete, you would need to know all of the geometry of all of the little pieces of concrete, and you'd need to think about all of the geometry of the treads in your tire, and that's hard. So what we've realized is that all of those hard things, I don't want to think about all the little bumps on pavement, right? I can approximate that in something that is pretty close to accurate for a lot of situations. So yes, as Porpoise says, you're pushing forward into tiny bumps and the bumps push back. But rather than doing a bunch of sines and cosines for every little piece of grit in pavement, this approximation that we're about to learn is pretty accurate. Yulin says, why does it sound so similar to more and more stuff can be described with fewer and fewer equations? Yes. So really what physics is about, this is kind of the thing that nobody talks about, but really what physics is about is figuring out ways to model things and then make approximations to solve those models that make enough approximations that we can understand the thing, but not so many approximations that we lose the essence of the thing. And that's really hard. That's what that's all of physics right there, is really understanding approximation. there is, I got an email today advertising a conference on something called effective field theory. And basically, effective field theory is a fancy way of saying the laws of quantum mechanics are too hard. We don't know how to calculate them. At best, we can use a giant supercomputer to sort of do it. But maybe we can come up with a way to make systematic the approximations that allow us to do this in a way that doesn't lose the essence of what we're trying to understand. Said Ferret Boy, that feel when we ignore air friction, but you're an aerospace engineer. Don't worry, air friction is coming back later. We're going to take some people on bicycles and we're going to send them down a mountain. We're also going to get some Teslas and see how far they can go on batteries. All right. So I'd like to treat these two cases one at a time. So first we're going to talk about kinetic friction, and then we're going to talk about static friction. So let's do that. I'm going to write some stuff here. We'll probably wind up erasing it. We'll write some other stuff, and then at the end of class, we will do a problem. That's our plan. So for kinetic friction, what we have is the force of friction opposes the relative motion and that the force of friction has this mathematical form. It's equal to some percentage of the normal force. So this is obviously the normal force. And mu sub k here, so this is called the coefficient of kinetic friction. And what it tells you is what percentage of the normal force is the force of kinetic friction. So let's talk about a brief example. So these coefficients are from 0 to 1, almost always. It's extraordinarily rare that they are greater than 1. So what's an example? Suppose I have some surface, and I have an object sitting on it with a mass of 100 kilograms. Maybe it's a big, we'll say it is a giant tank of liquid nitrogen, because I believe Alice right now is trying to move one into her lab. And this coefficient of kinetic friction here depends on the surfaces. So are friction and air resistance different, says Miles? Yes. So here we're talking about friction between solid surfaces. We will talk about fluid friction a little bit later. So in this case, suppose I tell you that this is moving that way. The velocity vector is to the right. So which direction would the friction force be? Opposite, yeah. So the force of friction here is to the left. And to calculate it, we would say, okay. Oh, and I need to tell you one other thing. I would need to tell you how sticky or slippery this interface is. So I might tell you that the coefficient of kinetic friction is 1/2, which is reasonable for a lot of objects sliding over the sorts of floors that we have. So in this case, the force of friction is the coefficient of kinetic friction times the normal force. Well, in this case, how big is the normal force? Well, that's just mg, which we could figure out by analyzing the forces in the vertical direction. So the force of friction would be 1/2 times mg, which would be 1/2 times 100 kilograms times 10 meters per second squared, which would be 500 newtons. So we'll just make a note here that mg would be 1,000 newtons. So the normal force here is equal to the weight. That's not always true, but it is now. So the normal force would be 1,000 newtons. So one way to think of coefficients of friction then is they tell you the percentage of the normal force that friction is. So if something is sliding, if two objects are rubbing past one another, which is different than rolling, rolling is more complex. But if two things are rubbing past one another, then the kinetic friction is always some percentage based on the coefficient of friction times the normal force. How did I get 1/2? Great question. We're going to erase this now. Nope. Too much friction when I was rubbing my eraser on the board. That's what happened right there. The kinetic friction of the board on the eraser was larger than the force that my fingers were applying to the eraser, and it came out of my hand. So in that problem, the coefficient of kinetic friction, and with all problems, depends only on the materials. And there are tables in your textbook of coefficients of friction for different things. So for instance, rubber on pavement, the coefficient of kinetic friction might be 0.8. But something smaller, so say steel on steel, the coefficient of kinetic friction might be lower. Don't quote me on these numbers. These are just estimates. And wet ice on ice, the coefficient of friction might be very low. So a higher coefficient of friction goes with surfaces that are stickier, and a lower coefficient of friction goes with objects that are slipperier. We will always give you those values. Or, maybe we'll give you what you need to calculate them. Yulin says, why does it take less force to keep a fast-moving object moving than a slow-moving object moving? In part because if an object is moving slowly, because it doesn't have much momentum, it will be brought to a stop more quickly by the same frictional force, I think. So yeah, SemSquatch has looked up stuff. So yeah, skis on snow might be 0.05. So a lot of engineering comes from trying to concoct materials to give you the coefficient of friction you want. So folks, I have just noticed that something has... Oh, here's a bad problem, y'all. This is the power adapter powering the USB-C hub running everything. And we're going to plug that in. My computer has drained its battery almost completely. that we are powered. Yeah, we seem to have power again. Yes. Whoop, one of my monitors is going in and out. What's going on? Well, hopefully it will fix itself. I don't need this to continue with class. I don't know what's going on, but let me click one thing just to make sure I can continue to see chat. Okay, everything is fixed. Sort of. Something's wrong with one of my monitors, but we can keep doing class. So this is kinetic friction. The next thing we need to talk about is static friction. Static friction, rather than taking things that are sliding and trying to stop them from sliding, static friction takes things that are stuck and keeps them stuck. So static friction, if I have, we'll write the words first, keeps things that are not sliding from sliding. So, for instance, if I have, I need a different color. If I have a blue box here with some mass, we'll put it again at 100 kilograms, sitting on a table. Now, you might imagine that if I were to, oh, I'm no more. You can't see. All right, it's frozen. All right, let me try to see what's going on. Can you all confirm that you can hear? You should be able to hear. I can fix this. Let me... Okay. Yeah, something has gone wrong with this USB hub. And the video capture was wired into it. Give me one moment. I believe I can fix this. Hello, everybody. Yeah. When I tried to fix the power issue, I think I also loosened a cable in the USB hub that also has the HDMI capture card. This is why the people who do professional video have little couplers that don't come off. And why us plebes teaching physics deal with USB cables that don't work. Are we back now? Oh, but we're not getting power. Okay, we're gonna lose everything in like 30 seconds unless I do something. So, folks, give me just, I'm so sorry. This is what happens when I move into a new space and use something different. I'm going to try to do something weird. You will lose me for just a minute, but I will be back. And I'm sorry this is happening right at the end of class. So you're going to lose me again. You should still be able to hear me, but you won't be able to see me until I reroute a few cables. I think the power is what I'm worried about. Okay. Now, I'm not going to be able to see... Okay, I'm back. Let me check one more thing. That's weird. Okay. I'm not going to be able to see Zoom chat for the rest of class. I apologize. It's kind of a desperate attempt to make sure things don't explode, and we've only got 5 minutes left. I'm not quite sure what the problem is. I know the frame rate has cratered. I'm just going to continue on as best I can for the rest of class. Yeah, I'm still here. I'm just having some sort of tech issue that I don't understand. Yeah, thanks, Adam. You could write anything that happens. Yes, thank you, Adam. I am so sorry, folks. Yeah, I think we're going to lose power in a minute, despite me doing what I did. The short version is I'm using a power supply that, for whatever reason, can't provide enough power. So, you know what? Here's what I'm going to do, because I think you're going to lose me in just a few seconds as my computer runs out of power. Here's what we'll do. You know most of everything you need for recitation tomorrow. There's one other piece of info that you will need. I'm going to record a short video this afternoon once I get all of my tech stuff ironed out, and that will contain the other things you need. It'll be maybe 10-15 minutes. Just take a gander at that tonight before you go to recitation tomorrow, and that'll be an introduction to what you need for recitation. I am so sorry. I tested this stuff yesterday. Apparently not well enough. So I apologize. We'll end class here so I don't lose the recording, and